Hey there, folks. So this is your instructor, and I'm trying something different this time, a pre-recorded lecture. So let's see how this goes. Okay, so this is the lecture on surface area. And to get started, let me remind you of what we did last time when we started talking about surfaces. For one, what the heck is a surface? Well, it's a shape that lives in 3D space. It's a two-dimensional shape. And usually when we talk about them, we use a parametrization of them. And a parametrization of a surface is a map that takes some subset of R2 into R3. And this was the picture that we drew for such a map. And I pointed out a few important components, namely the two tangent vectors, okay, T sub u and T sub v. And also, once we have the two tangent vectors, Tu and Tv, we can then take their cross product to get the normal vector to the plane, which we sometimes just call n. Okay, so that's all review from last time, and that's the setup for what comes next, which is surface area. Because if you think about it, computing surface area is sort of a natural question to ask, being as we've been computing areas and lengths and volumes this whole class. So this is the next logical progression in the topics. So I'm just going to come right out and give you the formula for the surface area of a surface S. And you can take this as the definition, although it can be justified. So we define the surface area of a parametrized surface S as described above as the double integral over the domain of phi, that is D, that is the subset of R2 where U and V live, of the norm of the normal vector. Remember that Tu cross Tv, that was the same thing as the normal vector, n. So we take its norm and we integrate that over the domain D in the UV plane. Now, this formula probably seems like it kind of comes out of nowhere, at least to some of you, and you can read some of the justification in the book. I won't fully justify it, but I'll at least say something about where it comes from, like where the heck does this term come from? The justification for where that term comes from a fact from linear algebra, which states the following. Let's say you have some parallelogram P that's spanned by two vectors A and B. So here's a parallelogram P, and it's spanned by two vectors A and B. Right, there's A and there's B. And when I say spanned, I basically mean like what you can see in the picture. Then it's a fact that is shown in theory in linear algebra. So maybe you saw this in Math 18, that the area of P is actually the length of the cross product of A and B. That is the length of n equals A cross B. So it can be shown that that's the area of P. And the book has some more details about this. And that's where this term in the area formula comes from. Okay, so now we've got the area formula. My plan is to do some examples. So I've got a few Fusili example. Check this out. Check out this parametrized surface. How about if we let phi of u and v equal u cos v, u sine v, and v? By the way, this is a lot like the cone example from the last class, where there was a u right here instead of a v. So the cone looked like a cone. When you change this to a v, you get a shape that looks like this, which should be familiar to all the Italians in the class. I myself am Italian, so you could say I'm a bit partial to a surface that looks like a fusilli noodle. Anyway, let's calculate the area of that surface. And so I'm going to do this live in class, but I encourage you to try it first. So you can pause the video now and go ahead and try it. Or if not now, at least give it a shot before we meet for class on Wednesday. Okay, so moving on now. Here's some special cases of the surface area formula. The first special case is that we have a surface that's a graph of some function of two variables. So suppose our surface is a graph, namely z is a function of x and y for x and y in some domain D. So the picture for this will look something like, so let's say here's D, lives in the xy plane. Okay. And then the surface is some graph above D. So I don't know what it looks like. Maybe it'll look like this. Maybe there's the surface S, okay? And there's a formula for the surface area of S in this special case. And here's that formula. It's not that hard to derive, actually. I'm not going to do it here now. But it's pretty straightforward to come up with this formula using the previous surface area formula. And this is also pretty useful because something I've mentioned before is that a lot of surfaces actually are graphs. Even if they're not globally a graph, you can often break them up into pieces that are graphs. Another special case that we have a special formula for is the case of a surface of revolution. There's actually two cases here, so I'll give formulas for both of these. One of them might be that we have some function where y is some function of x for x between a and b, and we revolve the graph of y equals f of x around the x-axis. So here, let me just take the mirror image of this and flip it upside down. Rotate, flip, vertical. There we go. So I think the rotated surface will look something like that. And there's a formula for what this surface area is. And it's given by this formula here. And this formula is not hard to derive. Again, using the previous surface area formula. You can see details in the text. It makes use of the path length formula, by the way, for the length of the graph of y equals f of x. There's another surface of revolution formula. So again, let's suppose that we have some graph where y is some function of f of x. This is just a one variable function again. And again, I'm going to make a surface of revolution, but this time I'm going to revolve it around the y-axis. So that's going to give me a surface that looks like this. Okay, so this here is the formula for the surface area of that surface of revolution. And it's kind of similar to the previous formula. You'll notice the key difference is that In the previous formula, the radius at a point was the y value, namely f of x. In this surface, the radius at some point is the x value. Hence, we have an x right here instead of an f of x. So either of these formulas can potentially be useful on a given problem. I mean, they'll not necessarily on the same problem, but I'm just saying, like, it's good to know all these formulas because occasionally one of them will be more useful than another. Although in theory, you can derive all of them from the initial surface area formula. So here's an example for the area of a torus, okay? For starters, fix some number big R, which is greater than 1. Consider the torus T, I'll call this torus T, which is parametrized as follows. The map phi is a function of little phi and theta, and it's given by quantity big R plus cos phi times cos theta, quantity big R plus cos phi times sine theta, and sine phi. So I had to look this up, but yeah, this is the parametrization of a torus, at least one way to parametrize a torus. And let me explain some of those parameters. So let's see if I can draw this. Let's see, there's the x-axis and there's the z-axis. And let me look at a cross. No, not there. This is hard to draw. Let's see. Okay. So there's actually sort of two radii involved in a torus. There's the smaller radii, which in this problem is just 1. So you could imagine that there's a 1 right there and a 1 right there. And then there's also the big one, which I call big R, and that's the distance from like the origin to the center of the little disk. So this distance right here would be big R. In other words, if you looked at a cross section, it might look like this. The distance from the origin to the center of the little circle is big R, and the distance from the center of the little circle to the edge is 1, the way I set things up in this problem. So that's the setup. Phi and theta are both allowed to range from 0 to 2 pi. I would recommend maybe just try picking some values of phi and theta and seeing what they correspond to on this torus. In fact, I can even get you started with that. I think right here would be where, let's see, phi is 0 and also theta is 0. And I think right here, that would be, let's see, theta is still 0, but phi is pi over 2, I believe. And I think if you were like right here, that would be, let's see, it looks like theta equals pi and phi equals pi over 2. Let's see. Yeah, that's right. But anyway, go ahead and check for yourself. And the challenge in this problem is to find the surface area of the torus. And after you do that, I challenge you to redo the problem using the surface of revolution formula that I showed you, because it's possible to visualize this, or maybe at least half of it, as a surface of revolution. You can use symmetry for this continuation of the problem. Okay, so I'll do those examples in class tomorrow, or well, tomorrow or today, depending on when you watch this, or maybe yesterday, heck, depending on when you watch this video. Anyway, thanks for watching, folks. See you soon.